Hello, welcome back to AIT 1102, Fluid Power Distribution. Today's presentation is going to be an introduction to Lesson 4, Hydraulic Actuators. In this presentation, we're going to describe what a hydraulic actuator actually is. We're going to describe hydraulic cylinder characteristics. We're going to identify hydraulic motor characteristics. We're going to identify schematic symbols for hydraulic actuators. And we're going to identify different types of hydraulic actuator failures, the causes of those failures. So as we've been going through this class, we've been concentrating on this one hydraulic schematic, and today's presentation is going to cover actuators. So in this circuit, our actuators here, we have a hydraulic cylinder and we have a hydraulic motor. So these are the types of components we're going to focus on today. So what is a hydraulic actuator? A hydraulic actuator is a device that converts hydraulic energy into mechanical energy. If you remember back to our pumps presentation, a hydraulic pump converted mechanical energy into hydraulic energy, and now we're going to convert that energy back into mechanical energy. There are two primary types. We have cylinders. They perform linear work, so we're moving in a straight line, or we have motors, which do rotational work. So the basic types of cylinders, your textbook goes into all of these types of cylinders. The ram cylinder, which is like a hydraulic jack you would use for lifting a car, single acting cylinder, double acting cylinder, telescoping cylinders, and the multiple mounting methods. For the purpose of this introduction, we're just going to cover the two primary types of cylinders, your single acting and your double acting cylinders that you find in a hydraulic circuit. The single acting cylinder, what makes a cylinder a single acting cylinder is that it uses hydraulic force or hydraulic pressure to move the cylinder in only one direction. So, for example, on this cylinder right here, your hydraulic fluid or your pressure would come in through this port here and actually fill this void and push the cylinder, the piston and rod, you would extend it. So you fill this up with pressure, or fluid and pressure, it's going to push your rod out this way. And there's no hydraulic pressure or fluid to actually return the rod or retract it. So in this particular instance, the opposing force out here on the rod would be what would actually retract the cylinder once the pressure was relieved on this end of the cylinder. Another type of single acting cylinder is where you have a spring return. So we have hydraulic pressure coming in on this side of the piston, which will extend the cylinder, and when this pressure is relieved, the spring tension or the spring pressure will actually push the piston back and retract the rod. So that's the two primary types of single acting cylinders. Now we have a double acting cylinder, and double acting cylinder, like the name implies, it's double acting. So we can put fluid on this side of the piston and actually pressurize this side, extend the rod, and while relieving the pressure on this side to allow the fluid to escape. And then to retract the rod, we could relieve the pressure on this side and apply pressure and actually retract the cylinder. So this type of cylinder has two ports, where the single acting cylinder only had one port. So you've got two ports to help you identify a double acting cylinder, and notice that it uses hydraulic pressure to move the cylinder in both directions. Another type of double acting cylinder is a double rotted cylinder. As you can see, it's a double acting cylinder, and you can identify it because it's got the two ports for the hydraulic pressure to come in. The only difference is now this one's got a rod on both sides of the piston, where the others just had the rod on the one side. So these come in, you'll find these on like a boom lift. A lot of times they'll have this type of steering on the front end. So this would actually move the front wheels back and forth on a man lift. Another thing that you might find on a hydraulic cylinder is a cushion. And what a cushion does, so if I have a cylinder and I just apply pressure to one side of the piston and extend it, this piston is going to extend at full speed, or if it has a flow control, the control speed, but it's going to go at the maximum speed that's allowed to go until it actually collides with this end of the cap, so it just kind of slaps into it, and that's what actually stops it. And the same thing on return. If you put pressure on this side and relieve the pressure on this, the piston's going to retract, and this piston's going to go back until it slaps the end of the cap, and that's what's going to stop it. So what they do to, as the name implies, cushion that last bit of the stroke, they'll actually have these, you'll see this area poked out here on the rod, and this will go into this area here and plug this off. So what happens, your cylinder is retracting, and it's retracting at full speed, and then once it gets so far, this will insert into this cushion, this area here, and seal this off, because your fluid's been going out through this larger orifice here, so this will plug that orifice, and then it'll force all the fluid to go through this orifice down here that's actually restricted. So it'll move real fast, it'll plug this off, and then in the last little bit of the stroke, it'll move real slow because the fluid's going to be restricted through this little flow control here. And this particular one is adjustable, so you can adjust it in and out to control how much you slow that cylinder down right before it gets to the end. And it keeps the piston from slapping into the cap really hard at a high speed. It slows it down and kind of eases it in, so it's not such an abrupt stop. And this particular example has a cushion on both sides, so when we're moving this, when we're retracting, we'll fill this void and force all the fluid through here. Or if we're extending, you've got this area, this wide area of the rod, so it's just coming through here, the fluid's going out here. When this gets in here, plugs this hole and forces the fluid through this restricted area to cushion the end of the stroke. And like with a flow control with a check valve, that's basically what you have in these cap ends. So when you're, let's say you're fully retracted and you've got this, so all your fluid would normally have to come through here. That's got a check valve here that actually lets it run full flow to get it moving, and until you unplug your cushion to allow the full flow into the into the cylinder, and so it cushions on the other end. And then the same way we're moving back, we've got a check valve here that opens when the fluid's moving back this way, so it's not trying to go through the cushion when you initially start the stroke. So that's just some different types of cylinders, some different things you might see that are more common in a hydraulic application. You might find in an industrial environment. Oftentimes you have to rebuild cylinders, and so there's some wear items in these cylinders. So this particular cylinder, you can see it's got 2 ports, so this is a double acting cylinder. It has cushions in here, so this has the slow it down at the very end, it'll cushion the end of the stroke. So, but what you've got inside here is you've got your piston, and on the piston you've got some rings, and these rings can be made of many different types of materials. But oftentimes when you rebuild a pump or rebuild a cylinder, you're going to replace these rings. There's a lot of times there's O-ring seals back here in these areas. Sometimes you can replace the cushion. I've seen some of those, sometimes the cushion will break and you can get in there and replace those. But the main thing you're going to be rebuilding is on here on the rod end, where you've got different types of seals and guides, where this is where the majority of your wear is taking place, and that's a lot of times what causes the cylinder to fail is you'll start leaking past these seals, and fluid will start leaking out past the rod, and kind of make a mess until it starts, unless you have a really bad leak, in which it could actually affect the operation of the cylinder. So this is just kind of an exploded view showing you the different seals and wipers and things that are inside the cylinder, that if you were rebuilding it, you would pull this gland out here to access a lot of these seals back in here, and you would replace these seals and end up putting everything back together. So just one type of cylinder, just kind of give you an idea of what they look like inside and the types of things that you would have to rebuild on a cylinder should one fail or start leaking. So as we said before, a hydraulic actuator actually creates work, or you can create force on an object. So 2 main things you want to, characteristics of a cylinder is, one, how much force can that cylinder apply, and how fast is it going to apply it? How fast is that cylinder going to move? And there are calculations for those. So we're going to kind of go through an example calculation of extending force, retracting force, extending speed, and retracting speed, and understand why those things are different on a given cylinder. So extending force is basically how much force or how much pressure you apply to the face of this piston here to force the rod out. So the formula for that is, the first thing you need to do is find the area of the piston, which you use the formula pi r squared, and r being the radius. So you measure from the center out of your piston to find the radius. You square that and multiply it times pi, and that will give you the total area of this face in square inches, or whatever your units are. We're going to use square inches. And then you multiply that times your pressure to get your total force for your extending. So for our example, we're going to have 1,500 pounds per square inch of hydraulic force, or hydraulic pressure, so 1,500 psi on a 4-inch cylinder. So this piston is going to be 4 inches in diameter, and this rod diameter is going to be 1 inch. So that's our specifications for this type of for this cylinder. So the first thing we're going to do is we need to find the area of this cylinder, or of this piston face. So we use our formula pi r squared. So we plug in our values, pi being 3.14 times the radius. So this was a 4-inch diameter piston, so we take half of the diameter, which is 2 inches, and we square it, and we come up with this equation. So you work out the math. So 2 squared is 4 times 3.14, and it comes up with the area, the total area of this piston face, that's 12.56 square inches. So now that we know the area of the piston, now we can use the rest of the equation to determine the force. So we take our area, multiply it times our pounds per square inch. So I mean, that's basically what we have. We figured out how many square inches. We know how many pounds per square inch, so you do your multiplication. And we find out that this cylinder, if we had 1,500 psi on a cylinder with a 4-inch cylinder bore, we're going to be able to apply 18,840 pounds of pressure on this rod, forcing it out. So that's how you calculate the extending. Now when we calculate the retracting, you kind of use the same thing, but there's an extra step that's a little different. So we have the same cylinder, so 1,500 psi on a 4-inch cylinder with a 1-inch rod. So when we were calculating the extending force, we used the whole face of the piston because we were able to utilize the whole face of the piston to put pressure on it. But when we retract, we've got the whole face of the piston minus the area that the rod's taken up, because the hydraulic fluid cannot act on that part of the piston face because the rod's is filling that area. So to calculate the retracting force, we have to take the hydraulic pressure times the area of the piston face minus the area of the rod. So that gives us the remaining area of the piston face that the hydraulic fluid can apply force to. So we've already calculated the area of the rod. That's in the previous step, we came up with 12.56 square inches. So now we're just going to figure out the area of the rod. We use the same formula. So this is a 1-inch rod, so we have to take the radius, which is 0.5 inches. We square that, which comes up to be 0.25 times our 3.14. So the area of this rod is 0.785 square inches. So we subtract this. So we have the piston face area, the area of the rod. So here's our formula. So we take our piston face, subtract the area of the rod, and multiply it times our pounds per square inch of hydraulic pressure that's retracting. You can see that we actually have a little less pressure or force in retracting because the rod's in the way of the piston face of being able to use the whole piston face. So extending, we were a little over 18,000 psi, and retracting, we're 17,662.5 pounds of force. So on this type of cylinder, we can have more force extending, then we can retract it. Now, if this was a double rodded cylinder like we saw in one of the previous examples, the force would be, if the rods were the same size on both sides of the piston face, the force extending and retracting would be the same. So just wanted to show that example that and the difference between extending and retracting. Well, speed, we're going to calculate in inches per minute. Your textbook goes in, I think gives a different value, but we're going to use inches per minute in this formula. So we want to know how fast this cylinder will extend given some parameters. So to figure that out, we need to know our formula. So our formula is the volume of the fluid coming into the cylinder times 231, which is a constant, divided by the area of the piston face. So our volume coming in is 10 gallons per minute. So that's our volume of fluid entering the into the cylinder is 10 gallons per minute on a 4-inch cylinder with a 1-inch rod. So we plug our values in. So 10 gallons per minute times 231 divided by our piston face area comes up with 2,310 divided by 12.56, or this cylinder, if we had 10 gallons per minute coming into this cylinder, it would move at 183.92 inches per minute. So that's how you calculate the extending speed. And the retracting speed is much like the when we're figuring pressure. You have to take into account this rod is filling part of this area as we are filling this area. So the retracting speed is just like on the other one, the volume times our constant of 231, and like when we're doing the force, we have to take the piston face minus the rod to come up with our new volume that we're trying to fill. So we take our piston face minus the rod area and divide that into the 2310 from our 10 gallons per minute and our 231 constant, and it comes up to be 196.18 inches per minute. So you can see, since we've got this rod in here, it's going to retract faster than it extends because there's less volume to fill because the rod's taking up part of the volume. So that's just some of the formulas. Like I said, your textbook will go more into detail in this, but I wanted to go through just a couple examples to show you how the formulas are solved. So now we've talked about cylinders. Now we're going to talk about hydraulic motors, which, like I said, provides rotational force instead of linear force. And hydraulic motors are very similar to hydraulic pumps in construction. They can have gears inside, vanes, piston configurations. So, like I said, if you go back to your pump lesson, you'll find these made very similar to the pumps. Instead of actually generating flow actually makes these spin. So hydraulic motor characteristics, what you have with rotational force, instead of linear force, you have rotational torque, which is units that we're going to use is going to be inch-pounds or pound-inches. It's determined by the pressure acting on the motor and the amount of volume or displacement that you have inside the pump. And motor speed is going to be determined by the flow rate of the fluid coming into the pump and the displacement of the pump. And we're going to work through a couple of those formulas as well. So let's say we have this motor here. We have 1,000 psi on the input side of the motor. The flow is 10 gallons per minute, and the displacement of this motor is 4.62 cubic inches per revolution. And if you remember back to pumps, when the pump was rotating, it would displace a certain amount of, or a certain volume of fluid, and motors work just the opposite. I mean, they have the chambers in here, and they can move, or so much fluid moves through in a given revolution. So for this example, the whole total volume of this area, if we made one full revolution of these gears, we're going to move 4.62 cubic inches of fluid. So to find our torque, we take the pressure times the displacement and divide it by 2 times pi. So, like we said, our pressure was 1,000 psi. Our displacement is 4.62 cubic inches per revolution, and then we divide that by 2 pi, and we start working our math down. Multiply these two together, and we come up with this pump with 1,000 psi would generate 735.67 pound-inches of torque. Speed, like I said before, speed is based on displacement and flow. So here's your formula for this one. And notice the 231 again is our constant. So we take our flow times 231 and divide it by our cubic inches per revolution. So our flow, 10 gallons per minute, times our 231 divided by our cubic inches or volume per revolution. Working on down. So this motor would spin at 10 gallons per minute. This motor would spin at 500 RPMs. So now we're into our schematic symbols. So we've discussed single acting cylinders and double acting cylinders. This is our single acting cylinder, and this is actually showing the 2 types that we discussed earlier. I've got one line coming in showing that it's a single acting cylinder. And there's nothing here to retract it, so whatever the opposing force is, whatever we're trying to move, would actually retract the cylinder. And this single acting cylinder has the symbol for a spring, so this would be a spring return single acting cylinder. Double acting cylinder, as you can see, is identified because it's got the 2 ports, so this shows that hydraulic fluid or hydraulic pressure would move the cylinder in both directions. And here's our double acting double rod cylinder. So this is showing that it's got a rod on both sides. It's got 2 ports, showing that it's a double acting cylinder. Then here is our double acting cylinder with a cushion. So we have these blocks here around the piston show that this cylinder has a cushion. And the difference between these two, this particular one just has a symbol or has a cushion on the extending side. So retract, there's no cushion. It doesn't show that there's a cushion back here. But if you remember this symbol here, this means that this cushion is adjustable. So whenever you see that diagonal arrow across the symbol, that tells you that it's variable or adjustable. So this cylinder has an adjustable cushion on the extend only. So motors, this is a schematic symbol for a hydraulic motor. And what makes this a schematic symbol for a hydraulic motor is the arrow is pointing in. If you remembered on pumps, the arrow pointed outward. So on a motor, the arrow points inward, and since this arrow is colored in, that tells me that it's a hydraulic. So the arrow pointing in, colored in, tells me this is a hydraulic pump. It's unidirectional, it's fixed displacement, because there's only one arrow on the inside here, and there's no diagonal arrow. And here we have a bidirectional motor, because I've got an arrow on both sides. They're colored in, which tells me it's hydraulic. And so since I've got 2 arrows, it tells me this motor to spin in 2 different directions. And then here we have our diagonal symbol, which tells me this is adjustable. So this is unidirectional, because I've only got the 1 arrow. It's a hydraulic, because that's colored in. And this arrow here tells me that it is variable displacement. So it'll be unidirectional, variable displacement motor. So back on our schematic, what we have here, this can be identified as a double acting cylinder, no cushions. And then here we have a unidirectional fixed displacement hydraulic motor. There's no variable displacement here. So that's the 2 actuators on this schematic, and hopefully that provides you a good introduction into hydraulic actuators. So Causes of failure for cylinders, things that would cause, over time could cause failures. Of course, contamination. You get contamination inside of the cylinder, any kind of dirt or grit, and so those piston rings that are running inside that cylinder, if you start getting dirt in there, it could start wearing into the cylinder's sleeve or in the piston face or the rings and cause premature wear, where you could actually start getting leakage past the cylinders or past the piston, which could reduce force, reduce speed, and actually cause it to the cylinder to bleed and drift. So, like I said, contamination gives premature wear, loss of speed or force, and can cause internal and external leaks, because if you get contamination, that contamination can be drug up on the rod past those seals on the gland end and start wearing those seals and start creating leaks. Mechanical failures, you could have broken rings, damaged seals, rod can break or separate from the piston sometimes. What you would see with a rod separating from the piston is you would be able to extend, and when you tried to retract, the piston would come back, but the rod wouldn't come with it. It's because it's no longer connected. Fluid temperature outside of operating range. Hydraulic fluid or hydraulic oil has an ideal operating range. If you start getting too hot, it could get too thin than the design specs for the piece of equipment you're working on, and thinner oil will move faster, so you could actually lose speed control of your actuators or your cylinder if the temperature was too hot or too cold. If it was too cold, the cylinder may not move fast enough. Causes of failures for motors, again, contamination can cause premature wear. It could wear the components inside the motor and causing internal leaks where you could lose speed or torque. It could cause leaks internal, could wear the seals on your the internal and external seals. Could have a mechanical failure. You could break a motor shaft, break a gear, piston or bearing could fail and start getting noisy, or could even lock the motor up. And again, fluid temperature, fluid gets too hot, flow more easily and could make things run faster than they're supposed to, or fluid that's too cold could make the motors turn slower than they should. So questions, if you have any questions, please go to the discussion board. You can post your questions there. Again, you can email me, call me, and I'll be happy to answer any questions that you have. Thank you.